delta H equals delta H minus T delta S. That's the first important equation I want to memorize. Second important one is actually delta G naught equals to negative RT natural log K. That's the second important equation. The third one is this one. The delta G equals to delta G naught plus RT natural log Q. These are the third equation that you need to memorize. So when we say the delta G naught is actually, we always need to put the concentration of all species inside my equation into like one. You have a very specific concentrations over layer, so you can calculate your delta G naught. But that's not the things we have all the time. Okay, the things we have all the time is actually with all different concentration for our species. So for equations, the things you can calculate is not actually delta G naught. Okay, you can still do all these calculations, but they will give you the delta G, not the delta G naught. And the delta G is related to your delta G naught through this equation. We know that delta G naught sort of actually describes how far away your system is actually from the equilibrium. If you today you did not actually do the things at the one end condition, you just do at random condition. It means actually that's how far away you are from the equilibrium if you're actually at the standard condition. And then the second thing is actually tells your current system how far away it is from your standard condition. By summing up the two, it actually tells you how far away your current system is from the equilibrium. So this is just something that I want to also bring up to your attention. So we know if your delta G is negative, okay, the reaction is moving toward the product side, right? What it tells you is actually if you calculate the Q of your reaction at current moment, it has to be smaller than your K, okay, because you want to actually move to the product side so that you can reach equilibrium, right? So that actually implies that your current Q is going to be smaller than your K. Because it's smaller than K, then you need to move to the product side, you actually bring up your Q, so eventually it's going to equal to your K. Okay, so let me say again, okay? If your delta G is negative, right, that means actually reaction is moving toward the product side, right? That means at the current stage, you don't have enough product. So if you calculate your Q, then your Q is going to be smaller than your K. Then it's going to move to the product side to bring up your Q, so eventually your Q is going to equal to your K. Another important concept you should have is actually if your delta G is equal to 0, that means your Q is equal to K. That means your reaction is actually at equilibrium. Very, very important concept. Okay, if your delta G is equal to 0, then your system is actually at equilibrium. Another very important thing from here is actually you should also translate these things backwards. If I tell you that the reaction is actually at equilibrium, then you should actually know that delta G is equal to 0. It is true vice versa. And then if you have delta G larger than 0, then you know the reaction is actually moved toward the reactant side. That means your current Q is actually you have too much product. So your Q is going to larger than the K of the reaction. So using this simple concept, I want to go through one question. What are the delta G and K at equilibrium at 25 degrees C for this specific reaction? So what's the keyword here? At equilibrium is the keyword, right? Because we know if you are at equilibrium, what's the value of your delta G? If you know this keyword, then you should know what it really means is actually delta G is going to equal to 0. So if I tell you that at specific conditions, the reaction is actually moving toward the product side, what is the value of your delta G? Should it be positive, negative, or 0? If the reaction is actually moving toward the product side, then you should know that your delta G is negative. If the reaction is moved toward the reactant side, then you should know that what it means is actually delta G is positive. Very important concept. You need to actually translate between all these numbers versus the statements. How are we going to use this specific reaction? Delta G equals to delta G naught plus RT natural log Q. So I'm going to give you one example. So in this question, it says, what is the delta G for the following reaction under the given condition at 400 K? So let's see your temperature. Will the reaction go toward the product, reactant, or at equilibrium? Right? So in order to know the answer of this, you should know that, okay, the things that you need to calculate is actually you want to know your delta G is either positive, 0, or negative. And it tells you for these reactions, that is the condition you have. It also gives you the equilibrium constant K for the specific reaction at specific temperature. Write out the three most important equations. Delta G equals to delta H minus T delta S. Delta G equals to delta G naught plus RT natural log Q. Delta G naught equals to negative RT natural log K. So one thing you can see very clearly is that it gives you the equilibrium constant K here, right? There's actually only one equation contain equilibrium constant K. Therefore, what this means actually is telling you the delta G naught. So you know that delta G naught is actually going to be known, okay, using these simple equations. And the things you also know that to make this judgment, you actually need to know your delta G. So you can calculate your delta G from either the equation 1 or equation 2. So apparently, you're going to use the equation 2, right? Because you already see delta G naught can be actually obtained. Now it's actually the only thing you want to figure out is actually your Q, right? Once you figure out your Q, then you can actually figure out your delta G. Then you can actually make a judgment. How do you actually write your Q? So for this reaction, N2 plus 3H2, that give you 2NH3. The Q is going to equals to the pressure of your NH3 second power, pressure of your N2 first power, pressure of your H2 third power. Do you have the pressure of your N2, H2, and NH3? You do, right? So you know this will be just 21 to the second power. N2 will be 4.2, and then H2 will be 1.8 to the third power. Okay, so if you do this calculation, you can get your Q is actually equals to 18. So now you know that delta G is going to equals to delta G naught is negative RT natural log K plus RT natural log Q. So your R is 8.314. Temperature is 400 K. Natural log your K is 41 plus 8.314 times 400 times natural log Q. Q is 18. Then you just compute all the things. Then in the end, you're going to get a value of negative 219.00 joule. Okay, so now you can see your delta G is a negative value, right? Therefore, you know the reaction is going to move toward the product side. So because your delta G is negative, therefore move to the product. So this will be the question you're going to encounter in your homework. So it's not complicated. So every time you see this K, then you know that actually tells you the delta G naught, right? But in order to actually make the judgment where the reaction is going to move to, you actually need to calculate your delta G, not delta G naught. So in that case, you're going to use the second equation. And most of the time, you're going to calculate your Q based on the information given in the questions.